So, welcome everyone. Thank you for coming just after lunch. I know it's hard to come just after lunch. My name is Marta Rybczynska. I will talk about the port of Linux we've done for a new architecture. But before I start, I'd like to ask you to bring back memories of your past. Bring back the memories of the computer architecture course you had a long time ago. Bring back the memories of registers, instruction sets, and things like that. It's not totally mandatory to understand my talk, but really it will help you with the examples, especially. So, when the memories are there, we can start. We can start from the definition of porting, because I've seen the people using the expression to port something for quite many different reasons. First is that when you have just a new board with an existing processors, with existing peripherals, and you need to adapt the software to run on this board. So probably it means that the peripherals will be mapped in different places, connected to different pins, stuff like that. Then the second way is to port to a processor from an existing family. You have a new SOC, you have a new version of the processor, and it means that you may have some instructions, some new instructions, you may have some modified instructions, you may have some things that work better, you may have some new peripherals, you may have the peripherals that have been changed. So you have to modify different things all around to be sure that it works as it should. And finally, there's the third version of porting, a porting to a completely new architecture. Completely new architecture means that the registers, they are different. You have a different number of registers. They are called differently. They have different purpose. You have a different instruction set. So all the assembly you need to learn once again, a different assembly. All the special things about the assembly of the architectures you know already, you have to change it. And in fact, that's this way of porting I will be talking about today. To go a little bit into details, when we have a new processor instruction set and the code is in C, you just have to recompile it if everything goes well. If there are some assembly parts, either built-ins or the assembly in lines, you will have to rewrite it for your new architecture. For the memory map, your memories probably will be in different places, and your peripherals will be either new or in different places or a little bit modified. So you will either have to configure the old drivers to work in the new way, or you'll have to write a completely different driver for every single new peripheral you have. And then when people create new architectures, they do not just create it for fun, normally. What they do is they create them because they have some new needs, and it means that the new architectures have new benefits. And a big part of working with new architecture will be to work with the new features, with the new optimization you can do, and apply the new optimization to the existing code. When it comes to Linux, there are certain things you'll have to work on when you want to have a basic Linux working system. This will start from the GCC, from the compiler, and be utilized. So things like a linker, on all the tools around that. I'm not a compiler expert, so I won't be talking about that. there are people who can do it much better than I can. But I will be talking about all the other elements. So the kernel, you will have to do the port of the Linux kernel, the basic port, the architecture directory basically, and all the drivers you will need. Then on the libraries side, you will need some kind of libc, the math library, pthread, and then everything else you may want for the application that will be running on the new platform. And then finally is the user space. Normally, those days, people will start with running BusyBox to have all the tools to test if everything is running fine, and then you go and port application by application. So the day comes, and, well, you do have a new processor. Bigger or smaller, but you have a new one. So the first thing you will have to do before trying to write any code will be to learn about your new architecture. So now we'll get through the Kalray K1 architecture we have used for a port to understand what we are dealing with. And we are dealing with something pretty advanced. This processor has 256 cores in one chip. So it's a massively multi-core with, in fact, it has a little more than 256, but that's a detail. It is all software programmable, high performance, of course, and it's also a very low power one. And finally, we have a rich set of peripherals like the PCI Express, like Ethernets, and different things like that. And now, when we go deeper into the architecture, because of scalability reasons, the processor is divided into groups of cores. So you have groups of 16 groups of 16 cores that share memory and have one big peripheral network on chip. You have probably heard, maybe you have heard about it on your computer architecture course. And there are 4 groups of so-called I/O cluster cores. Those are 4 quad-core SMPs, pretty typical quad-core SMPs, that have access to all the typical peripherals, starting from PCI and finishing at the flash or SPI. And then this, each core of this processor uses the same instruction set. It's a very long instruction word. Just to explain it shortly, it means that it can run up to 5 instructions in one cycle. It has some interesting instructions like bitwise logic unit that can do NDNS changes quite effectively, and many other things. It has hardware loops without branch penalty. It has, every single core has MMU. It has idle mode and a floating point unit. Now, to port Linux to that architecture, there are quite many things that are important. I've marked them on the slide. Pretty much everything is important when you're porting Linux to it. With the small exception of the floating point unit that is not that important in the Linux kernel. In the user space, it is. Now, every journey starts from a first step. In this case, it starts from an empty directory that we'll have to fill later on. But the first step is there. And to have the first version running, in fact, personally, I was surprised. Because finally, you need much less than you would expect that you need to have. And let's go through. You need the code to do the processor startup, to configure the caches, configure interrupt vectors, all that stuff. That is pretty dependent from the architecture, and you have to go through the core manual to find out exactly what you need to do. Then, configuration of the memory allocators, depending on how much memory, where it is, and how you are going to use it, how the zones are on this architecture. And the third big part, interrupts, exceptions, and syscalls. All the assembly parts you will need to have, and the support C code to handle that. There are some things that are also important, so the device tree and the kconfig, the basic stuff. And personally, I prefer to have the first console also in the basic port, just at least to have the print K out, just to see something happening. And that's it. OK, there's some things to write, but now how? For the basic part of the boot, there's not much documentation, but it exists for some parts. For the SMP, there's pretty rich documentation. For the atomics, there's pretty rich documentation, but just for the start part from the boot, for the basic configuration, not much. So what people do, and you can find traces in all of the architectures, they go and they copy-paste. When you are copy-pasting, the choice of the architecture you are copy-pasting from is quite important. What I personally prefer is to go to the simple architectures and to the recently merged architectures and copy code from them. I wouldn't go to x86 or to ARM directory. There's way too much stuff. And the third option you have, if you cannot find the code that fits your use case, is to go through 2 or 3 architectures, see how they implement the given features, and then implement it yourself. Documentation helps. From time to time, you will have to search for other architectures manuals. And in fact, as a result of all that, I can currently read assembly of some architectures I have never used in my life. I even don't know where they are used, but I can read the assembly. And when we are at assembly, some interesting thing we've seen when porting Linux to the K1 architecture, you have an assembly example on the slide, is the side effect of the architecture being a very long instruction word. It can run multiple instructions in one cycle, but it also means that if you are writing assembly, that's you who's going to write the right instructions in the right places, so it works as it should. Our GCC port handles this quite well, and you can gain a lot of on performance if you put the instructions correctly. So it's OK to put 2 or 3 instruction groups manually, but for longer parts, it's becoming painful, and especially if this is the code you're going to modify later on. So what we did as a result, that we really do compiler built-ins at every single possible place, and we just write the assembly when it's absolutely needed. And as a result, we have probably the lowest assembly concentration in the port everywhere. I'm quite sure of that. And now you have done your work, and that is a success, you know? It is a big success, because it means that kernel has booted. It tried to find init. It didn't find it. But that is pretty normal, because there is no init in the initial file system at that point. So let's go and let's create some init. To have init, you'll have to have libc. So if you do not have a port yet, that's the right moment to do it. What we have done was the uclibc port, why? Because UClibc works very well with BusyBox, and we wanted to have BusyBox as fast as possible. But that may be a personal choice. There's not much difference in time you use to port one or the other. And then the first init really make it statically linked, because otherwise you will have to do all the compile and linker work to have the dynamic loader running. And that takes time. Just for first testing, not really necessary. And then libc is fine, but you will have to start your application. So that's also the time to clean up the ABI between the kernel and the user space. First thing is the process setup when it wakes up at the first place. You need to define which values are in which registers when the process wakes up. For example, where the stack is, where the main function arguments are. All that stuff, it requires work in the kernel and in the libc in parallel to make it work together. Other thing is that you will have to work on the syscall list, on the syscall numbers, and on the ways the arguments are being passed to the syscalls. So how many arguments you can have in your syscall, how you are going to pass it through registers, through stack, in some other way. That all needs to be cleaned up and documented if possible. And the third thing, signals. You will need some basic support of signals, but in fact, if you do not have applications that really use signals, you do not really have to worry too much about this. And signals are the most complicated part of all that. Now, what we have used to debug this, we have used the instruction set simulator for our architecture. On one side, you have the console over instruction set simulator output. So that's typical print K all around the place. And on the other side, you have the output of the execution trace from the instruction set simulator. We are lucky because our instruction set simulator, it can show every single instruction with a value in every single register. That's pretty handy if you have questions about how this register, how this value got into this register. So either manually or analyze these tools, and you find out everything. It's pretty handy for debugging. It's really pretty fast for debugging. And the instruction set simulator has been a great help when doing the port. Then we'll have some first init out there. Some basic notes about the executables. I would prefer to have the static executables running well at the beginning, then work on the dynamic linker. That requires, in our case, quite much work on the compiler side, and also on the bin-util side, much less on the kernel side, in fact. And then some basic drivers you will want to use for the basic boards you have. So, I would say the consoles and the main peripherals you will use. But testing is something people easily forget. Especially at the beginning of the port, it's pretty important for me to be sure that all the modifications you are doing, they do not break the things that work already. We've tried multiple methods to do the early debug. So what we've tried at the beginning was to create unit tests from parts of the kernel code but that was pretty complicated to compile and pretty complicated to maintain. So we've pretty much abandoned that. And what we moved to is a test, so-called test init. It's a very small init that can be put in the init.ramfs file system. And it runs all the basic functionalities needed. So it opens files, it interacts with some drivers, it does some basic things, and it's short enough that there are no problems running it in the simulation. So we have the basic validation that all the tools, the libc, and the kernel, they do work correctly in this configuration. That avoids having something that works just partially. And what we've also developed are some visualization tools. This is a small dump of the high-level view. This is just about the activation and disactivation of kernel threads during the boot. This kind of debugging we've done to see if the scheduling is working more or less correctly, to do visual inspection of the trace. We also do have much more advanced versions of that. One of my colleagues is presenting quite often at the Eclipse conferences. The tools are pretty powerful. So the basic tests are fine. Then there are some later tests. It's normal developer's idea to go and write your test on your own. But the thing is that if you just want to test all the syscalls, you have some months of work, I think. And then you need to have references. What are the right behaviors? What are the wrong behaviors? And in which case? So instead of that, we moved to using real existing test collections. What we are using is Linux Testing Project. It's something very interesting. It's an active project, a very active project, in fact. There are tests for nearly everything. And they are good. We have had some problems with the UC Linux versions for some of the tests. I've submitted some patches. I still have some patches pending for that. But in general, it's really much better than to write everything on your own. And then, I don't know how many of you will recognize this. I do, but I don't know. This is a fragment of strace output. And strace, I will use an example. An example, what you can do when you are implementing some new functionality. By new functionality, I mean either you are activating a new kernel subsystem, or you are activating some new file system, or you are activating a new driver. So what you will have to do is to activate the kernel option, fix everything that doesn't compile, then implement everything that's missing, do some works in the kernel headers because it may be missing some parameters that need to be passed to the user space, and do the libc work there. What worked really well for us was test-driven development in this case. It's pretty nice. In the strace case, just to explain for those who do not remember or have not used it for years, strace allows you to see which syscalls are run by a program. It shows which parameters are passed to the syscall and what's the result of the syscall. So it's much less verbose than a complete output with all of the instructions. So it's becoming interesting during debugging when you start having more than one process running in your system. And it also allows simple visual inspection if you have had some errors, for instance, coming from some syscall, and because you are missing some rarely used syscall or something like that. Pretty handy. strace is using some ptrace calls, and it's used signals. So in fact, till this point, you really can live without signals. If you want to use ptrace, you really have to make it work properly. So how we've done that? There are some ptrace tests in the LTP, so we've used them. We've made the LTP tests for ptrace running, and then we moved to the strace code. The strace code itself, it compiled quite easily, but it didn't work. Why it didn't work? Because there are architecture-based defines in the strace code. So what we had to do is to go through the code, find out all the defines, and implement everything that is needed and that is missing. So that's the way to go when you're adding a new feature. You have a new architecture, you have some special things for this architecture, and then how to make work the big things. The big things, in our case, were the SMP, so the symmetric multiprocessing, and the MMU, memory protection unit. The thing is that in both of those, there is much left to the architecture than for other features. You do have a lot of space for your own design to fit it right to your architecture. So those are the things that take time, and they take also design to implement. Fortunately, at this level, there's already documentation. Personally, I find that the documentation for SMP is much better than documentation for MMU, but that's a personal opinion. So apart from the typical kernel subsystems, we have two special ones that are pretty special and pretty particular for our architecture. First is the network-on-chip subsystem. It's a network that's connecting groups of cores in between them. Of course, there is no subsystem Linux kernel for that. So it's pretty much invention from the beginning. It has taken a lot of discussion on our side, and many tries to make it work as we wanted it to work. Also because the network on chip is really the main performance point of the architecture. So this driver, it really has to do the things right. The other particularity of our architecture is that depending on the core you are on, the same address in the memory map of a peripheral brings you physically different peripheral. So you are right, you are using the same address. Depending on the core you are on, you may be driving a different pin. So as everyone is talking about device trees, in our case, it was pretty complicated to put that into the device tree. And then, of course, when you are getting mature, the distribution part. You can do it yourself. That's fine if you have 3 packages. If you are going above 10, it's becoming less funny because you need to look up for all the parameters to pass to compilation for every single packages. There are many people who have done that before you, so it doesn't really make sense to retry and redo the same thing. What we are running currently is the build root because it was pretty easy to set up. And we are looking at Yocto to use it in the future. And then some lessons I find important for people who may try one day to port Linux to other architecture. First thing is that it's a very good idea to divide your port into stages. Why? Because you can see progress. You can see something working. It's much easier to debug, and it's much easier to concentrate on one single functionality instead of trying to implement everything at the same time. Then, don't forget to test, and test from the beginning. At the beginning, there are some subtle things and subtle bugs you can introduce. If you are not testing, you won't find out when the problem appeared for the first time. Linux kernel has pretty nice generic headers. Really, most of the architecture features you are able to get from the generic headers. And that's fine for the beginning. Then, if you need something more optimized, you deactivate the generic part, and you re-implement it on your own. And then keep the coding style right from the beginning. Pretty hard to change afterwards. What I'm doing quite often currently, is that I put a lot of panics all around. When I add a new functionality, I put panics in all non-implemented functions. Why? Because it's easier to see if the code got to the not tested path. Of course, those panics never get to the user finally, because with enough tests, I will get into all of them before. But it really helps. It saves time, because you may simply forget that there is some specific option that it got through, it shouldn't. Simply don't waste time debugging things that are not really worth debugging. The same in the user space with exit if it doesn't work. And as I've shown you in the asterisk example, I really prefer code that doesn't compile for a new architecture than code that compiles, but then you have to grep inside to see why it doesn't work. It's also losing time for nothing. So if you do have an application that is independent, that has some architecture-dependent part, really, please, if you do not support different architecture, just make sure that it doesn't compile. It will be easier for the first person who tries to port it somewhere. And then I like the idea of creating new debugging techniques for if you need them. New tools, if you need them, pretty much what we have done. Read documentation. Read also comments in the code. It's a form of documentation that's normally right. And when porting Linux to a new architecture, you'll have to read code from other platforms. There's not enough documentation to do without it. So that's it for now. If you have any questions. Yeah?
So how long it took?
The question is how long it took. It depends. It depends which part. Just to have the first thing running with first in it, just on the kernel side, it was something like 2 months. Then other things, it takes much more time.
You plan to submit it upstream?
The question was if we mean to put it mainstream. Yes, I would love to as soon as possible. You know, when you are not mainstream, you have some nice situations from time to time. One example will be the 3.8 kernel when it tried to update to 3.8. Someone, and I don't want to know whom, has changed the pointer type in the TTY functions. It compiled. I really don't want having things like that. Yeah. Some other questions? Yeah?
How contained is your port to the architecture specifically? So once you had to change engineering code?
Could you please repeat? I haven't heard the beginning of the question.
How self-contained is your port? You have to change much engineering code?
The question was how much self-contained the port is. We have no changes in the generic kernel. It's all in the architecture directory.
Which architecture have you chosen to copy and paste?
The question is which architectures we have chosen to copy-paste from. At the beginning, it was mostly Microblaze and Blackfin. And then some new architectures got in, basically OpenRISC, Metag, as something else, I think. They are pretty simple, easy to read, and they are right. They are done right. They have been cleaned when they were included, but that's another story. But they are pretty easy to understand and to work with.
Was the VLIW instruction brand new for this chip, or did you have some other VLIW before?
The question is if the instruction set was new. Yes, it's a new instruction set done for this processor.
Did you have any interesting debugging with the VLIW optimization?
The question is, yeah, if we had some interesting debugging issues at the because of the multiple instruction in the same place. The compiler handles it well. The compiler problems have been solved before, mostly. The problems can happen when you are passing between the C code and the assembly. And that was something that was happening, and that is happening. And for that, the instruction set simulator output with exactly every single value, it's great because you just see what went wrong. Any other questions? Yeah?
So is Linux sort of your main workload for this processor? Or is it a side project? You usually use other software for like your product cases? Can you talk a little bit about that?
Okay. So the question was if Linux is the main use case for this processor. The thing is that port of Linux, it takes time. And we needed something to run on the processor before. So what we are running currently and what people are using currently is RTMS, which took much less to port. And the Linux is currently under productization. So it will be shipping soon. Any other questions? No? Thank you.